So there are qualitative descriptions for solution concentrations, and these words mean what you think they mean. A dilute solution means there's not very much dissolved, and a concentrated solution means there's a lot, and these are just relative terms. And then there are many, many quantitative measures of solution concentrations, and here are some of them. Why are there so many? Because they are useful in different situations. So, like the city that tests the water and sends out their water quality report, they're going to report a lot of things in the parts per million or parts per billion region. And that's useful because it gives them a nice, it's like maybe 1.7 parts per billion. Well, you express that in molarity, and you've got this ridiculously small number. Chemists tend to use molarity because we're interested in moles because of our chemical reactions, and we've got the mole ratio, and so we're always converting things into moles, and so we express solution concentrations as moles. Mole fraction and mole percent are also useful in some situations. This is a really weird one. Molality looks like a typo, but it's not. That's a weird one. I wish we could ignore it, but we can't. So, quick review of molarity. Molarity is the amount of solute in moles divided by the volume of the whole solution in liters. And this is like the most important concentration unit in chemistry. We really, really need to understand what molarity is. It's discussed more thoroughly in section 5.2. That was a long time ago. The thing about molarity is that it changes slightly with temperature. So as you heat a solution, the moles of solute don't change, but the volume of the solution changes. Because most liquids, as you heat them, they will expand. And so if the volume's getting larger, that makes the molarity smaller. Most of the time this doesn't matter, but there are situations where it does. So that's the point of molality. Molality is not temperature dependent. So here we have amount of solute, again in moles, but this is divided by the mass of the solvent in kilograms. Not the mass of solution, the mass of just the solvent. The mass of the solvent doesn't change when you heat it up, and so molality is constant. This is has an abbreviation of lowercase italicized m, not to be confused with a non-italicized m that's meter. That's not confusing at all. Usually you can tell from context which one is intended, meter or molality. Parts by mass and parts by volume are used in lots of different situations, medical field, engineering, general population. So parts by mass, here we're looking at the ratio of the mass of solvent to the mass of the solution. And then it's going to be multiplied by a factor. So percent by mass, remember percent is the part over the whole times 100. So here it's the mass of the part, the solute, divided by the mass of the whole thing times 100. Percent literally means per 100. We can take a percent by mass, like 14% by mass, and we understand that that has 14 grams of solute per every 100 grams of solution. So that's a really useful conversion factor. Sometimes percent isn't the best unit because our concentrations are very small, and so then we can use parts per million or parts per billion. Percent is parts per 100. So these are just larger quantities. So ppm, parts per million, mass of solute divided by mass of solution again, times a million, parts per billion, that same fraction times a billion. So if we see something like 15 ppb, 15 parts per billion by mass, that means 15 grams of the solute per billion grams of solution. Same pattern works for parts by volume, but here we're measuring the volumes of the solute and the solution, and again, multiplying by a factor. This is typically used more for solutions of liquids. But 22% ethanol by volume means 22 milliliters of ethanol in 100 milliliters of solution. The unit that you use here for volume is not critical as long you just have to use the same unit for both. So this could be liter and liter, or microliter and microliter. You can even use English units. I'm not sure why you would want to, but you could. So let's do some example problems. What mass of sucrose in grams is contained in 355 milliliters of a soft drink that is 11.5% sucrose by mass? Assume a density of 1.04 grams per milliliter. Many of these come down to dimensional analysis, and I think it's always a good idea to try dimensional analysis before you go on to equations or algebra. So we read the question and we pull the numbers out. So I've got 355 milliliters. We've got different parts here, right? We have the sucrose, that's the solute, and then we have the whole solution, which I'm just going to call it soda. Okay, so 355 milliliters of soda. The 12 ounces there is just kind of a FYI, because if I say, well, how big is 355 milliliters, you probably go, I don't know. But if I ask you how large a 12-ounce can of soda is, you're like, oh, I know exactly how big that is, right? I even maybe know how many gulps it's going to take to swallow the whole thing. 355 milliliters is the same as 12 ounces. But we're not actually going to use the 12 ounces. Then we've got 11.5% sucrose by mass. So 11.5% sucrose. Written that way, it's not all that useful. We need to write it in a different form where we can see that it's a conversion factor. So this by mass means I have 11.5 parts sucrose per 100 parts of soda. So 11.5 per 100. And it's mass, so I need a mass unit. I'm just going to use grams. So 11.5 grams of sucrose per 100 grams of soda. That's what percent means. And then I've got a density 1.004 grams, right? This is a vertical fraction per milliliter. What's that the density of? The solution, right? The soda. So that's 1.04 grams of soda in 1 milliliter of soda. So those are the numbers we're given. And then we have to ask ourselves, well, what are we trying to find? Mass of sucrose. Mass of sucrose in grams. So I'm trying to find grams of sucrose. I need to know what number to start with. And here I think the units can be really helpful. If I look at this first one, 355 milliliters of soda, could that be used as a conversion factor for anything? Well, how is that related to grams of soda? Well, the density would be useful as a conversion factor, but this volume here is not useful as a conversion factor, right? It's just a volume. This one looks like a conversion factor, and the density looks like a conversion factor. So that tells me that 355 milliliters is probably the thing I'm going to start with. So I'm going to start with that. And then I have to figure out, well, how am I going to get... Well, that wasn't a good idea. How am I going to get to grams of sucrose? Well, I could go from milliliters of soda to grams of soda, right? Because that's what the density gives me. And then I'm trying to figure out how can I get from grams of soda to grams of sucrose. Well, those are the units on this percent concentration. So there I have my path, milliliters of soda to grams of sucrose. And from that I can write out my equation. 355 milliliters of soda. I have two arrows, so I'm going to have two conversion factors. This one's going to be grams of soda, and then grams of sucrose. I'm going to put milliliters of soda down here. And grams of soda over here. Is this dimensional analysis the same stuff we did at the very beginning? So this one here relates grams of sucrose and grams of soda. That's the last term. 11.5 grams of sucrose. So I put 11.5 in front of grams of sucrose and 100 grams of soda. And then the density, 1.04 grams of soda per 1 milliliter of soda. Okay. I know some of you are still a little iffy on dimensional analysis. Lab today would be a great time to ask me about that. It's still very beneficial for you to figure it out. Pardon me? That sounds about right. Yep, that's what I got. So calculator's saying 42.458 grams. And then sig figs, right? So 3 sig figs here, 3 there, 3 there, 3. So 42.5 grams. Yeah. Any questions? This should be a pretty straightforward problem. Right? No, they're not. But there will be some like this on the exam. Definitely. So 42.5. Yeah, it could be on the final. A water sample is found to contain the pollutant chlorobenzene with a concentration of 15 parts per billion by mass. What volume of this water contains 5 times 10 to the 2 milligrams of chlorobenzene? Assume a density of 1 gram per milliliter. Okay. When we read these problems, they don't necessarily seem very straightforward, right? But we've learned that we can do problems that we didn't think we could do. Right? And so we don't read it and go, I don't know what to do. So, well, I'm going to work at it. I'm going to write the numbers down. I'm going to see what I can do with them. So we've got 15 ppb. ppb stands for parts per billion. And it says by mass. So, whoops, I wanted an equal sign there. So that means 15 parts per billion parts. A million is 10 to the 6. A billion is 10 to the 9. So this is the chlorobenzene. And the solution is water with a teeny tiny bit of chlorobenzene in it. So I need a unit there. It needs to be a mass unit. Generally, grams is going to be the easiest. So 15 grams per billion grams. Then they've given me this number 5.00 times 10 to the 2 milligrams of chlorobenzene. Benzene. Yeah. Gotta finish that word. And then they're giving us a density That's the density of what? Water. So 1 gram of water per 1 milliliter of water. And what are we trying to find? Yeah, the volume of water that contains this amount of chlorobenzene. It didn't specify a unit. What might be a good unit to use? Liters? Sure. So we're looking for liters of water. You got a question? Parts by mass and percent by mass. Parts by mass is a more general term because that includes percent by mass, parts per billion, parts per million, parts per trillion, anything. It depends on what you're multiplying it by. Percent is always part over whole times 100. So if I'm trying to get to liters of water, and I'm probably going to need to start with one of these things, what looks like it's not a conversion factor? This milligrams of chlorobenzene, right? That's not a per unit. The rest of them are this per that, this per that. So that's what I want to start with, milligrams of chlorobenzene, and then I'm going to try to get to liters of water. Why is this water down here? Assume a density. What's a little confusing here is that the water sample, the water is actually the solution. Because it's not pure water, it's like tap water. It's got other things dissolved in it. Yeah. So if it would help, we could call it the solution instead of water. Will that help? A little bit? So let's call it that. Because we, typically when we talk about water, we're talking about pure water, and then we're specifying what we're mixing it with. So, solution. That's the water. So this is per grams of solution, and the density of the solution in grams per milliliter. So I have my starting point, milligrams of chlorobenzene. I have my ending point, liters of solution. And I have to figure out how I can connect these. So I don't see milligrams in any of these conversion factors. I actually don't see liters either. I see milliliters. So if I got to milliliters of solution, I could go to liters of solution, right? And if I'm starting with milligrams of benzene, I could go to grams of chlorobenzene. I'm going to start calling it CB because that's a long word to write out. CB, chlorobenzene. I can do those two conversions just knowing what metric prefixes mean. And then I need to get from grams of chlorobenzene to milliliters of solution. Well, this is giving me grams of chlorobenzene to grams of solution. And the density is grams of solution to milliliters of solution. Remember that day I got the index cards out and made these little domino-like things? That's what we're doing here. We're just taking these pieces and figuring out how can we piece them together to make a path. So milligrams chlorobenzene to grams chlorobenzene to grams solution to milliliter solution to liters of solution. Lots of arrows. Each arrow is a factor. So 5.00 times 10 to the 2 milligrams chlorobenzene. Times, in a line, I'm going to grams of chlorobenzene. And then I'm going to go to grams of solution. And then I'm going to go to milliliters of solution. And then I'm going to go to liters of solution. So milligrams down there, grams down here. Get all the units in there first. So we rewrote 15 parts per billion as 15 grams per billion grams of solution. So that's going to come in here where I have grams of solution and grams of chlorobenzene. Grams of chlorobenzene are on the bottom, so that's 15 grams of chlorobenzene for a billion grams of solution. A billion is the same as 1 times a billion. The milliliters of solution and grams of solution, that relationship comes from the density. There's 1 gram of solution in every milliliter of solution. And then my first and my last terms are just metric conversions. So I recognize that milli means 10 to the minus 3. Here I have 1 milligram. 1 milligram is equal to 1 times 10 to the minus 3 grams.
So we could just stop at milliliters of solution?
Could we stop at milliliters of solution? We could. If this was open-ended, it's not specifying what unit. Milliliters is a unit of volume, perfectly fine. If it's multiple choice, look at the unit that's given. This one I happen to remember from yesterday, it gives the answer in liters. So we're going to go ahead and go all the way to liters. So 1 milliliter in the bottom, 1 times 10 to the minus 3 liters on top. So what are you getting? I'm getting 3.3 times 10 to the 4 liters. And you say, well, that's a lot of liters. It's 3,000 liters. Sorry, 33,000 liters. But if we want 500 milligrams of this compound, and there's only a teeny bit in the water, it's going to take a really large volume to get 500 milligrams. Any questions? .3 times 10 to the 4 liters. Mole fraction and mole percent. These are similar to parts by mass, but here instead of mass, we're looking at moles. So the mole fraction is the amount of solute in moles divided by the total amount of the solution in moles. So that's the solute plus the solvent. The fraction is what you have before you multiply by 100 to get the percent. So a mole percent is just the mole fraction times 100. Mole fraction is typically abbreviated with the capital Greek chi, to the fancy looking X. So chi solute, that's the mole fraction of the solute. Okay. A solution is prepared by dissolving 50.4 grams of sucrose in 0.332 kilograms of water. The final volume of the solution is 355 milliliters. Calculate the concentration of the solution in each unit. Molarity, mole fraction, molality, mole percent, and percent by mass. You said you liked these. Here we go. Well, what's molarity? Moles per liter, right? Moles of solute, here the solute is sucrose, per liter of solution. Well, do we have either of those values? Well, we have the volume of the solution in milliliters. Right, we've got 355 milliliters is the volume of the solution. So we can convert that to liters. .355 liters. And then we need moles of sucrose. They gave us grams of sucrose, right? But we can convert grams to moles. 50.4 grams, C12H22O11. Hey Siri, what's the molar mass of sucrose?
The answer I found is 342.116 atomic mass units.
So grams, we want grams on the bottom, 342.1 grams per mole. So 50.4, turn the calculator on. 50.4, come on. 50.4 divided by 342.1. 0.147, 3 sig figs in this, 32 moles. I really don't want to round this to 3 sig figs because I'm not done with the calculation. If you round it to the correct number of significant figures, it'll probably turn out okay. If you round it to fewer, things could go wrong. You could end up with the wrong answer even though you did the right kind of calculation. 0.14732 divided by 0.355. So 0.41498. This is moles per liter. Molarity, or 0.415 molar. Any questions? On to part B, mole fraction. Mole fraction is equal to what? The moles of the part divided by the moles of the whole. So the moles of the solute, which is the sucrose, divided by the moles of the entire solution. That's moles of sucrose plus moles of the solvent, which is water. Well, I already calculated the moles of sucrose, so I can stick that in there, 0.14732. And then that's going to show up in the denominator as well, because I have to add the moles of sucrose to the moles of water. How do I calculate the moles of water? Well, I get the mass. I get the mass of water. So 0.332 kilograms. I'm going to convert that to grams. And then to moles using the molar mass of water. 0.332 183 divided by 18.2. Push the wrong button. That's better. 18.423. Should also have 3 sig figs. And that's the grams of water. Sorry, not grams, moles. So that's what I'm going to put down here, 18.423 moles of water. Now I just need to be careful when I do this on my calculator because I've got a quantity added in the denominator. 0.14732 divided by, open the parentheses, 0.14732 plus 18.423, close the parentheses, press equals. And so this is giving me 0.007933. Should have 3 sig figs. A fraction doesn't have units because the units in the numerator were moles and the units in the denominator were also moles, and so they cancel out. So that's unitless. Molality. What's molality? So this is moles of sucrose, the solute, divided by the mass of the solvent in kilograms. So kilograms of water. The reason it's kilograms, a kilogram of water is very close to 1 liter of water. They're pretty much the same size when the density is 1. Okay, so we are going to use our moles of sucrose again. And divide by the mass of water, which they gave us, 0.332 kilograms. So this is going to be 0.444 molal, or moles per kilogram. Any questions? Mole percent. This is the mole fraction times 100. We already calculated the mole fraction. What's this guy up here? 0.00793 times 100. And we get 0.793%. And one more, percent by mass. So percent by mass is going to be the mass of the sucrose, grams would work, grams of sucrose divided by grams of solution. So that's grams of sucrose plus grams of water. And it's a percent, so we multiply by 100. So we've got the mass of the sucrose, 50.4 grams. And we're going to divide by that 50.4 grams plus the mass of the water. This is in kilograms, so that's going to be 332 grams times 100. $13.1799 with 3 sig figs, that's going to round to 13.2%. So all these concentrations are describing the same solution, but the units are different, so the numbers are a little different. Any questions? There's the answers in slightly out of order. I'm not sure why, but so we should be able to convert between concentration units. What's the molarity of a 10.5% by mass glucose solution? Well, 10.5% by mass. That means 10.5 grams of glucose per 100 grams of solution. And I'm given a density 1.03 grams per milliliter. That's the density of the solution. So I'm trying to find molarity. Molarity is going to be moles of sucrose per liter of solution. So I look at where do I start, and both of those numbers have per units. But guess what? What I'm ending up with has per units also. So then what do we start with? Well, I'm finding a concentration. I should start with a concentration. This is a density. This is a concentration. I want to start with the concentration. So I can do this as a fraction, a compound unit, and convert grams of glucose to moles of glucose. And in the same equation, convert grams of solution to liters of solution. And do it all in one calculation. And students who are going to appreciate that don't really need me to tell them how to do it. So I'm going to show you how to do it a different way. And you're like, well, that just sounds messy to me. Well, what if we just take this numerator and convert grams of glucose to moles of sucrose? That would be a trick. Yeah. Converting one sugar to another, sorry. This should be glucose as well. So we'll do that, and then we'll convert grams of solution to liters of solution, and then we'll divide them. So I'm going to take the 10.5 grams of glucose, and I want to convert to moles of glucose. Hey Siri, what's the molar mass of glucose?
The answer I found is 180.16.
So 10.5 divided by 180.2, 0.058268 moles. And 100 grams of solution. I want to convert this to liters. So I'm going to go to milliliters, and then I'm going to go to liters. So the density I was given was 1.03 grams per milliliter. So 1.03 grams is equal to 1 milliliter. And then I'm going to use the meaning of milli. That's 1 times 10 to the minus 3. And this is going to come out to 0.097087 liters. So the molarity then is the moles divided by the volume in liters .600 moles per liter. Any questions?